Hello, we're back with the prone positioning and ARDSnet protocol PowerPoint, and we're going to start with video 2 now. In this video, we're going to discuss the distribution of pulmonary blood flow, pulmonary vascular resistance, Pucelle's law, lung zones, and cardiac output. So for the distribution of pulmonary blood flow, gravity has a lot to do with it. Because of gravity, the interluminal pressures of the vessels in the lung bases are greater than the pressures in the apex. And I actually have a hand-drawn picture of that I'll show you in a second. And as the vessels widen, the vascular resistance decreases and the blood flow increases. So basically, the blood is gravity dependent, which means that it's naturally going to fall down to the base of the lungs, which means that the bottom of the lungs is going to be more perfused than the top of the lungs. The blood's going to flow a lot better through there. So the high interluminal pressure in the lung bases will cause the vessels to widen, which is what that second bullet point is about. As they widen, because of the high interluminal pressure, the vascular resistance decreases, the blood flow will increase. So pulmonary vascular resistance. When the vascular resistance increases, your blood pressure will also increase. And this in turn will increase your ventricular afterload. And all of this I'll discuss in just a second what it means. The pulmonary vascular resistance equation is your mean arterial pressure divided by your cardiac output. Normal for a pulmonary vascular resistance is going to be less than 2.5 millimeters of mercury per liter per minute, or there's another unit of measurement, and it's 200 dynes per second per centimeters. So you can see either of those interchangeable, but that's the normal for it. And next we have Pucelle's law. This law states that the blood flow is enhanced as the vascular system widens. Basically what I was just talking about, the interluminal pressure. The wider the vessel, then the more blood that can flow through it, kind of like a water hose. If you squeeze the hose, less water can get through it. And then that calculation is just going to be the flow equals the pressure times the radius of the tube raised to the fourth power. This law is due to gravity affecting the interluminal pressures, causing the vessels to widen, as I said. So then for the lung zones, I have a picture on the next slide over, but I'll just kind of explain which each zone is for now. Zone 1, the alveolar pressure exceeds the systolic pulmonary artery pressure while the alveoli are maximally distended. This means the pulmonary capillary is completely compressed. This zone is not typically seen in your healthy lungs. So your alveolar pressure is going to be too high because they're compressed all the way. In zone 2, this is going to be the middle of the lung. The alveolar pressure exceeds the venous pressure, which compresses the pulmonary capillary. So your systolic pulmonary artery pressure is greater than the alveolar pressure, but your diastolic is not. So blood will only flow through the pulmonary capillary during systole. When the heart is contracting, it's only going to flow through when it's opening up. And then there's zone 3, which is in the base of the lung. So the alveoli in the base of the lung are not distended, so blood flow through the pulmonary capillary is continuous. The little air sacs aren't open all the way, and so there's no compression on your pulmonary capillaries. The blood can flow through without interruption. Both your arterial and your venous pressures are greater than your alveolar pressure because of the gravity. And so then here is a picture, and I also have it right here. So like I said, zone 1 is at the top. There's going to be little to no blood flow up there. That's due to gravity and the pressure differences. Your alveolar pressure is going to be higher than your arterial pressure, which is higher than your venous pressure. In your zone 2, you're going to have intermittent blood flow because your alveoli are somewhat distended, but not completely. So your arterial pressure is going to be greater than your alveolar pressure, which is going to be greater than your venous pressure. And then at the base in zone 3, your continuous blood flow is occurring, where your arterial pressure is greater than your venous pressure, which is greater than your alveolar. So the determinants of cardiac output, your equation for that is going to be your cardiac output equals your stroke volume times your heart rate. Your stroke volume is determined by 3 things: the ventricular preload, ventricular afterload, and the myocardial contractility. The ventricular preload is when the myocardial fiber is stretched during diastole and it contracts more strongly during systole because of how far it's been stretched. This means that the myocardial contractility will be greater because it's being stretched to the max. Ventricular afterload is the force against which the ventricles must work to pump blood. This is determined by the volume of or viscosity of the ejected blood, peripheral vascular resistance, and the total area of vascular space that the blood is being ejected into. And then myocardial contractility is the force generated by the myocardium when the ventricular muscle fibers shorten. So when contractility increases, it's going to, or it decreases, your cardiac output is going to do the same. So if it's contracting more, then you're going to have a better cardiac output. And if it's contracting less, then you're going to have a lesser cardiac output. So just to cover this video real quick, we went over the determinants of cardiac output. We went over the lung zones. We went over Pucell's law. We went over pulmonary vascular resistance and pulmonary blood flow. And thank you for watching.